We're going to explore ANOVA and see how it works using the F statistic. We're looking at some data of babies, and we said babies vary. How much of that variability is just sort of inherent within groups of babies relative to how much variability is there between groups of babies when we organize them into different categories? This is in ANOVA. Does the mean of a continuous variable differ between a multi-level categorical variable? How ANOVA works is through a statistic called the F statistic. And in fact, sometimes it's called the F test. What you need to know, and it's very simple, is that F is a ratio of that variability between the groups, which we've been thinking about vaguely as some sort of signal. You like that analogy? Some students do, some don't. Okay, well, it's a ratio of the signal relative to the noise. And, that's kind of what all statistics is you're trying to look at patterns and see if those patterns are due to chance or if there's something there. We're sort of hardwired to do stuff like this. If you look over there and you look at those leaves, is that a tiger or is it just a bunch of leaves? Well, if you're not good at doing that stuff, you get eaten and then you don't pass your genes along and then you don't have kids who are good at that stuff. So you are good at this stuff. Is there a pattern amongst the noise? Is there a signal out there? And that's really what F is, the F statistic. So if the F is higher, if F is how much difference is there between the groups, in other words, how much can we attribute to this factor relative to sort of how much inherent variability is there within a group? Remember, babies vary. The bigger the F, the more of a signal. And so we can summarize our data with F as a statistic. Remember, a statistic is a number that describes your sample. And then we can see, is F weird? What would we expect to get for F if the null hypothesis is true? This is all the same idea of hypothesis testing. We turn F into a p-value, and then we see is p greater or less than our cutoff for statistical significance. Let's see how this F works. This is a great applet that I want you to play around with, and you can see the difference of between group variability relative to within group variability. Let me walk you through this. Here we have some data that looks like it could be analyzed by ANOVA. We have 3 groups, and we're looking at the mean of some outcome. And this gets summarized with the F statistic that you see at the bottom of the screen, which in this case is the between relative to the within. And in this case, if you just look at the data, it looks like something is going on. The group in the middle is lower than the other 2 groups. So the means are not all equal. Now, the great thing about this applet is we can play around with the data. Think for a second, if we're going between relative to within, what happens if we change the bottom, the denominator? What if we make that within group variability bigger? Well, if we make that within group variability bigger, see how the points now are more spread out? There's bigger standard deviation. You can click on that top slider bar and play with it. What's happened? Well, between the groups, it's still the same, but the within group is bigger. F statistic is thus smaller. And if F goes down, P goes up. And this, in this case, this would not be statistical significance. What if that within group variability is really tight and that denominator is small? I can change the standard deviation and make it really tight. This would give me a much larger F statistic if you look at the between over within. If F is high, P is small. In this case, it's very small. What was that for? Tantalizingly close to statistics? No, this is very small. And so we would reject the null hypothesis that all means are equal. Now, remember, the other thing that really plays a role in here is the sample size. Look here, I have 20 in each group, and it's 0.03. What do you think will happen as my sample size goes up? Well, I'll change that here. As my sample size goes up, what happens to my F statistic? You see more of a signal, better able to hone in on those true means, right? Less of a standard error around them, and then the p-value goes down. If I have a small sample size, let's see if we can go to a small sample size, 7 in each group. You see now that the means are about the same here, but I don't have as good of a spotlight or as good of an idea of where those are. Let me go back to the slides and now summarize this applet. So by experimenting and playing around with this, what you can see is that when you have that bigger sample size, you have a better sense of where the truth is, more precision, and you'll have a lower p-value, more likely to find statistical significance. When that standard deviation goes up within each group, that's the within, right? That's the denominator. And so your signal might be the same, but there's more noise. And here your p-value then is higher. As the differences get bigger, now look at where these means are. You have the mean of this group, the mean of this group, and now you get this low mean of this group. As you change these means, now you are changing F equals between over within. As you change these means, that signal gets bigger. As your signal gets bigger, F goes up. As F goes up, P goes down. Some of these applets that you can find will actually let you play around and change the means. On this applet, you can actually take these little groups. They look like cocktail hot dogs. You can slide these up and down, and you can increase the size of each of those, and you can watch that F statistic go back and forth as you have the between relative to the within. So play around and experiment. There's so many good applets and simulations online. If you're a visual learner, if you learn through this sandbox and this experimenting and actually seeing how things change, avail yourself of those resources. So we get an F statistic and one number summary of our data. And now we have to sort of convert that or turn that into the currency of the p-value. What the F distribution is, the nice thing is your computer will do this for you. It will look up what the appropriate F distribution is. And there's an infinite number of them. It depends on how many groups do you have and how many observations do you have. And the computer will take your F statistic and plot it on a given curve. And guess what curve it is? It's the curve of if the null is true. So here, for example, is an F distribution for a certain set of sample, a certain study design where the degrees of freedom would be 4 and 12. And then if your F is high, well, what's high? Well, it depends. What's weird? What's my cutoff? If your F is high, you color in the area to the right, and that turns into your p-value. So again, if the null is true, what would you expect to get? It turns out that if the null is true, you would expect to get something around 1. Imagine behind me, I had 4 boxes lined up, A, B, C, and D. And I walked around to the other side of the room and I just took a bunch of babies and I just chucked them at the wall. What would it look like? Well, you would get some babies here and some babies here and some babies here and some babies here. And the variability between and within, they cancel each other out and they'd be about 1. They'd be equal. But if there starts to be some sort of pattern, can I erase these dots? Oh, cool. Yeah. If there starts to be something different like this, now that's a signal. And as that signal gets up, F will go up. And as F goes up, I get results that are more and more weird or unlikely, or results where the probability of seeing them, if the null was true, would be less and less. The p-value gets smaller and smaller. So the F test or the F statistic is how you quantify the data from a one-way ANOVA convert it into a p-value, and say, do we have evidence to reject that null hypothesis of all means being equal? And we'll see what happens next if we decide to reject the null hypothesis and say, there's a difference in here somewhere.